9 here. So chapter 9, which now has been a week since we started it, so I want to do a quick overview of the more important concepts that we covered, especially towards the end. All right, we talked about electrons in atoms and how the initial model, actually if I go all the way back, the initial model proposed by Bohr was that there were these set orbits for the path that the electrons took around, kind of like a moon orbiting a planet. So very specific paths. I think even on one of these slides I drew like the Jimmy Neutron kind of logo, if you remember that, right? The electrons follow paths. Well, that worked for hydrogen, right? So hydrogen had these specific emission spectra. So there are only specific wavelengths of light, which we also talked about light, wavelengths, frequency. But those could be predicted using the Bohr model for hydrogen, but not for anything more complex than hydrogen. So we moved from this idea that there are these specific paths taken to orbitals. So general areas where the electron is likely to be. Because the electron, unlike a moon orbiting a planet or baseball taking a specific path, doesn't move like that. It moves randomly, and it never takes the same path twice, essentially. Which led us into the quantum mechanical model. So in the quantum mechanical model, we have these orbital shells. So n equals 1, n equals 2, n equals 3. Those are our principal quantum numbers, and they specify principal shells for energy levels of electrons around a nucleus. There are 4 different types. The first one, and I want to go to this slide, is the s orbital. They're spheres, so every time you move from 1s up to 2s, that's a higher energy level. That sphere is a little bigger. You go from 2s to 3s, it gets a little bigger again. But we have other shapes as well. So the next orbital that we came across starts at n equals 2, and those are the p orbitals. So p orbitals have these dumbbell shapes. There's 3 of them, and they occur in all 3 of the sort of principal axes, x, y, and z. And again, like our s orbitals, if you go from 2p to 3p to 4p, every time it's the same shape, it's just a little bigger, a little bigger, a little bigger. Higher and higher energy. Then if you get all the way up to n equals 3, we add another type of subshell, and those are the d orbitals. We're not going to do anything with f orbitals, although if you do go to n equals 4, there are f orbitals. So for every principal quantum number, there are that many different subshells. So at n equals 1, all we have is s. At n equals 2, we have s and p, 2 different types of subshells. N equals 3, we have 1, 2, and 3 subshells, at least up to 4. So when we go to n equals 3, the d subshells, again, have their own unique shapes. And there's 5 orbitals there. So they're all sort of this, 4 of them are this crossing pattern. So it's kind of like 2p orbitals if they were crossing, 2 dumbbells each. And then this last one, which is the dumbbell with a donut around it. And that's where I told you that these electrons can move from one point in these orbitals to another point without crossing any of the space in between. Then we talked about electron configurations. So if you were to go through and try and figure out where these electrons are supposed to be, right? So each of these electrons for an atom has a location, an orbital, that it's most likely to be found. And every time you add another electron, it goes into a new orbital. Well, actually, they can pair up in orbitals, but each one has a spot. And so we use our electron configuration to say that we're in for hydrogen here, the n equals 1 principal quantum shell. It's in an s orbital, and there's 1 electron in that s orbital. So this continues on. If we did helium, for example, these are orbital diagrams. So instead of just writing as a small number what number of electrons there are in the orbital, we give them these little half arrows. And then you can only have an electron of each spin in an orbital. So 2 electrons total, and they have to be opposite spins, which is the Pauli exclusion principle. As we got more and more complicated, you start filling more and more of these orbitals. And the order that we fill them in is from lowest energy to highest energy, because the electrons don't want to be in high energy orbitals. Kind of like when you fill a cup with water, some of the water doesn't stay floating at the top of the cup, it all goes down to the bottom. But here we've got specific spots where they can sit. So as you fill these in, you're moving from one orbital, actually I should have done it this way, to the highest orbital, or to the next highest orbital. So stepping up those one at a time. This gets a little bit weird once you get to 4s, because 4s is actually lower in energy than 3d. So we fill 4s before 3d, but we come back to it. So did an electron configuration for carbon. And there's a couple ways that you can do this. One of them is to just look at the periodic table, say, okay, carbon, and again, remember the number at the top right of each of these cells for each element is the number of protons. For the neutral element, so with no charge, they have the same number of electrons as they do protons. So if carbon has 6 electrons, then we can say we've got 6 electrons, and we start filling these in, starting with 1s, then 2s, then 2p. And you'll see that each of these, if we add up these superscripts, they add up to 6. So we've accounted for all of the electrons in carbon. We also talked about Hund's rule, so filling orbitals with equal energy. You fill them singly first and with parallel spins. And this is where I have the example of Mrs. K's chemistry land. So you can think of these different orbitals like hotel rooms with different numbers of beds. So the S rooms only have a single bed, and you can put 2 people per bed. The P rooms have 3 beds, and you can put, again, 2 people in each bed for a total of 6 electrons. But they're going to fill each of those beds one at a time first before they have to share. So here again for oxygen, just look at the periodic table. So oxygen has 8 protons, so it has 8 electrons. And then we just filled those in on this orbital diagram. That's just a little fancier of an orbital diagram showing the exact energy levels. One of the ways that you can sort of remember these and what order to fill them in is by drawing out this sort of little schematic. This is really easy to draw because you just start a column of 1s, 2s, 3s, 4s, and then a column of 2p, 3p, 4p, and then 3d, 4d. And you could keep going with each of these columns. And then when you're trying to figure out which electron orbitals you need to fill or what order you need to fill in, you move at a diagonal. So we start with 1s, then we go to 2s, then we go to 2p, to 3s, to 3p, to 4s. And this also brings about the skipping 3d and filling 3d only after we filled 4s. So without having to memorize it, all you got to do is remember, write a column of the s orbitals, and then the p orbitals and the d orbitals, and where they start, and then fill at a diagonal. You can also look at the periodic table, though, to figure out what order to fill in these orbitals. So we talked about how these different parts of the periodic table, which you can actually see the different colors, that's nice, correspond to different types of orbitals. So all of these elements have their highest energy electrons in an s orbital. Everything in the middle has its highest energy electrons. So the last electron you fill in is in a d orbital. And the pink over here, yeah, it's pink on there, those all have their highest energy electron in a p orbital. So you can look at any of these on here. You can see nitrogen is actually the third element, so 1, 2, 3 into the p block. So its highest energy electrons are going to be in 2, because each row of the periodic table corresponds to the principal quantum number. So our highest energy is going to be 2, and it's in the p block, and it's 3 elements into the p block, so it's 2p3 is the last orbital you would fill. And I think that's about where we got to. So to double summary, lower energy orbitals fill before higher energy orbitals. Orbitals can hold no more than 2 electrons. They have to have opposite spins. And when you're filling orbitals of identical energy, so like the p block or the d block, you fill them one at a time first, all with the same spin, and then you come back and you start doubling up if you still have more electrons. Alrighty, so let's put this into practice now. So we're going to write the electron configurations and orbital diagrams for nitrogen, oxygen, fluorine, and neon. We start, we're writing out these element symbols: nitrogen, oxygen, fluorine, neon. So for nitrogen, I actually just told you this one. There's 2 ways that we can do this. We'll do it the first way that I told you about, where we just count the number of electrons. So nitrogen has how many electrons? 7 electrons, right? 7 protons, 7 electrons. So if we got 7 electrons here that we need to fill in, we always start at 1s. So we have 1s, 2. So we've used 2 over 7 electrons. And then our next orbital is going to be 2s. So 2s, and again, it only gets 2 electrons. So now we've used 4 of our 7 electrons. And our next orbital is going to be 2p. And we're going to put our last 3 electrons into that orbital. So it would be the electron configuration for nitrogen. Then if we want to do an orbital diagram, we make either boxes or lines. This is going to be 1s. It's going to be 2s. And then 2p actually has 3 suborbitals. And in some ways, it might be easier to start with this first, because you could just simply write out a few of the boxes. And like I just showed you, you can see from the periodic table where you're going to have to stop. Right? So nitrogen's in the 2p block, so we're going to stop in 2p. And then you say, okay, I've got 7 electrons. These are going to go 1, 2, 3, 4, 5, 6, 7. So we just filled all of those electrons in. And our electron configuration and orbital diagrams should match. So 1s2, we have 2 electrons that we drew into the 1s orbital. 2s2 also drew 2 electrons into the 2s orbital. And then 2p3, showing 3 electrons in our 2p orbital. Ow. Okay, from nitrogen now, let's switch it up a bit, and let's try and just use the periodic table to figure out what orbitals we're going to fill. So if we look for oxygen on the periodic table, I guess I could gesture to this one sometimes too. What block is oxygen in? It's in the p block. So our last orbital is going to be p. So we can go back to the beginning of the periodic table. And for hydrogen, what orbital is hydrogen's one electron in? S. So hydrogen would be 1s1. Helium is 1s2. So we filled the 1s1, the 1s2. What's lithium? 2s1. Beryllium would be 2s2. And then boron starts our p block. So it'll be 2p1, carbon's 2p2, nitrogen's 2p3, which we just wrote out here. So oxygen is 2p4. So that means all of the electrons really that are in oxygen are represented on the periodic table by all of the elements that come before it. So we can see that if we're past hydrogen and helium, our 1s orbital is going to be full. So it'll be 1s2. If we're past lithium and beryllium, our 2s orbital is going to be filled. So it's 2s2. And then oxygen is the fourth element in the p block. So it's going to be 2p4. All right, so for fluorine, what would we write first if we're going to write out the electron configuration for fluorine? One s2, 2s2, 2p5. So it follows this exact same pattern every time, because all of the elements have the same orbitals. We're just filling up different numbers of them. We're filling them up with different numbers of electrons. And the periodic table is arranged in such a way that, moving from one element to the element to its right, you add just one more electron. And so you fill in one more electron for your electron configuration. So then what would neon be? 2p6 would be the last one. But then 1s2, 2s2, 2p6. So now we can actually, oh, sorry, I didn't do the electron orbital. I made that too big. So these are all going to look the same. The only difference is going to be, I'm actually going to use that row that I wrote there, the 1s2. Those are representing for all of these. So if we fill these in, they're going to look exactly the same, except, at least for this series, we're just adding one more electron for each one. So you can imagine now, if we wanted to write out an electron configuration for something like lead, which is number 82 on the periodic table, that's 82 electrons that we would have to place in orbitals. And that would take a long time. It would use a ton of space. Instead, what we can do, though, because, like I said, if we're past any element on the periodic table, it's going to have the same electron configuration plus a few more electrons, however many elements it is past that other element. Does that make sense? So we use the noble gases as shortcuts. So let's say we wanted to do chlorine on the periodic table. That's 17 electrons. But instead of writing out 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 3s1, 3s2, 3p6, 3s2, 3p6, right? So instead of writing all of that out, we can instead just use neon and say, everything before, same electron configuration as neon. We filled all of those up. we have the same number of electrons as neon, plus, now we start, and chlorine's in the third row. So that's N equals 3. So it's going to be 3s2. Sorry, we're doing this for chlorine. And it's going to be 3p5. So neon has 10 electrons. So same number of electrons as neon, plus 2 in our 3s orbital, and then 5 in our 3p orbital. So 7 plus 10 gives us all 17 electrons placed. So it is the same pattern over and over and over again. If you keep on moving from element to element to element, you could write this out. You could write out the electron configuration for all of them. It would be good practice. But you also don't have to, because you can take shortcuts. All right, so for sodium, again, it's in the third row. So what noble gas would we use to abbreviate the electron configuration for sodium? Neon. So whenever we want to abbreviate an electron configuration, you go up one row and then to the noble gas, which is at the very end. So if you were in row 4, which starts with potassium, ends with krypton, you would use argon as your shortcut. If you were in row 6, or sorry, 1, 2, 3, 4, 5, sorry, row 5, which starts with rubidium, Rb, you would use krypton as your shortcut. So we always use the noble gas before. So for sodium, then, this gets really easy. So we start with neon. And then how many more electrons do we have than neon? Just one. So where do we put that electron? 3s1. So yeah, we can take some shortcuts in representing these locations of electrons. Are there any questions at this point? No? Cool. Let's do a few more of these. Okay, so for aluminum, where are we going to abbreviate? Neon again. Okay, and then we have, well, even without counting the number of electrons, more than neon that we have, we can figure out what our orbitals are going to be just from the periodic table. So looking at aluminum's position on the periodic table, it's the first element in the p block. And then the only things between aluminum and neon are going to be sodium and magnesium. So it's going to be our, again, 3s, 2, and then 3p1. So essentially we're saying start from neon, and then these are the orbitals that are filled in. So for bromine, where would we start with bromine? Argon. Okay, so then bromine gets a little bit trickier now, but not too much trickier. So between bromine and argon, how many electrons do we have? 17. So we have 17 electrons in there. So starting at potassium, so we have potassium and calcium. So that'll be our 4s. So we have 4s2. And then you have to remember that the D block, even though it's in the fourth row, is always 1 minus the row that it's in, or the row number minus 1. So if we're in the fourth row, that first D block is actually 3D. How many electrons do we have in the d orbitals? So it's 3D. That's our principal shell and our suborbital. How many elements are between calcium, so starting with scandium, going all the way over to zinc, in the D block? 10. So there's 10 elements in there. Those represent those 10 electrons in the d orbitals. So it's 3d 10. And then to go the rest of the way across the p block to bromine. And this is, again, remember, d is always weird. It's always off by 1, it's 1 less than. We go back to 4p. And then we have 5 more electrons there. So it's 4p5. So we can also look at, say, bromine should have 35 electrons. And so we have argon, which has 18. So 35 minus 18 is 17. And then counting our adding our superscripts up here, we have 2 plus 10 is 12, plus 5 is 17. So we have all of the electrons that we should have. Oops. All right, last example here. For strontium, we start our abbreviation at krypton. So again, we're just going to the row above, and then all the way down to the end, which is the noble gas. So we can put in brackets, krypton. So this is again where the nomenclature comes in handy, remembering what these elements' names are from their symbols. And then how many orbitals, how many electrons are we filling in? 2. In what orbital? Yep, 5s2, which is a lot shorter than writing out everything that comes before, or trying to count them all the way up. Is everybody good on that? Excellent. We did neon. Okay, so if we write an orbital diagram for argon, we could actually abbreviate our orbital diagram. We're not going to. So remember, orbital diagrams are just another representation of the electron configuration. So instead of just saying how many electrons are each suborbital, we're actually showing how they're, I guess it's a little bit confusing if I just call it, showing how they're configured. We're showing how they're arranged in those orbitals. So for argon, if we're going to write everything out, we always start at 1. So this will be 1s. Then our next orbital will be 2s. What's our next orbital after 2s? 2p. And if you want a way to remember how many boxes you should draw for each orbital, there's 2 ways that you can think about this. One is that each box holds 2 electrons. So if you think the S block is only 2 elements wide, that's 2 electrons that it's representing, so that's 1 box. The P block is 6 elements wide, representing the 6 electrons across there, so there's 3. The D block is 10 wide, so divide that by 2, there's 5 orbitals for the D block, or 5 boxes that you would write in here. Or you can also just think it's 1, 3, 5. Is that a chord? Yeah. Sorry. So 1s, 2s, 2p, then we jump up to 3s, 3p. Do we need to go any farther for argon? Yeah, we can stop there because argon's at the last element in the 3rd row. So its highest principal quantum shell is going to be 3p. And then we can just fill in all the electrons for argon. So argon has 18 electrons. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it does have a full complement of electrons. Every one of those orbitals is full and paired. So this is actually, for elements, this is a special state. When you have all of your orbitals filled and paired, it's a lower energy state than if you had even just one less or one more electron. These electrons in the highest, or the outermost principal shell, are called valence electrons. This is a super important concept because it's the valence electrons that are interacting with other elements. At the beginning of this, you probably don't remember because it was last week and there's been an exam in between, but ask the question, why is hydrogen reactive? Why is helium not reactive? And it's because of valence electrons. So it determines, right, these are the ones involved in chemical bonding. It determines how they form bonds. And electrons that are not in the outermost principal shell are called core electrons. They don't matter so much because they are in the core. They're not on the outside. Right? If you, there's going to be an analogy for this. I guess I was thinking of how like a jawbreaker, because it's got layers, but it's always the outer layer that you're interacting with on a jawbreaker. Eventually you get to the inner layers. So these valence electrons are determining why things are reactive. We're going to look at an electron configuration for silicon. So valence electrons. Valence electrons occupy the highest principal shell. So remember, our principal shell is the number that's in front of the S or the P. So these are, or this one is 1s, so it's in the first principal shell, which is the most inner shell. Outside of that, we have 2s and 2p, but those are still inside of the 3s and 3p. So you can identify from an electron configuration what your valence electrons are based on this number in front. If the principal number is the highest, all of the electrons with that same principal number are going to be your valence electrons. So here we have 4 valence electrons. And the rest are core electrons. So let's write out for chlorine. And again, I think the periodic table is the easiest way to do electron configurations. Basically, everything that it's past is going to be one of the part of the electron configuration. Right, so we're past hydrogen and helium. So that's 1s2. Move down to the next row. So we're going to be starting at 2s, because we're past lithium and beryllium. So that's 2s2. And we're even past boron through neon, which would be our 2p. There's 6 there, so we're past 2p6. That brings us down to the next row. So we're now at 3s2. And we go over to the p block again for 3p5. So how many valence electrons does chlorine have? 7. So looking at all of our principal quantum numbers, 3 is the highest. So these are our valence electrons, and the rest are core electrons. Oops. Now, if we wanted to, we could have abbreviated for chlorine by writing neon first, and then 3s2, 3p5. So not only does, right, because neon is the noble gas at the end of the row above, not only does abbreviating make it easier to write out electron configurations for elements farther down the periodic table, neon actually represents all of the core electrons. So the valence electrons are only the ones past that. And as I mentioned before, the valence electrons are the ones doing all the work. So I don't really know, it doesn't really matter about the core electrons. So if we think about this looking at the periodic table then, the column that the element is in tells you how many valence electrons it has, because that's how many valence electrons it has past the previous noble gas. And that also corresponds with these alternate column numbers that we give what are called the main block elements. So 1A and 2A, obviously being columns 1 and 2, 3A through 8A, starting over at 13, if you're to count all the columns, but 3A through, helium. So if I ask you, how many valence electrons does fluorine have? Well, what column is it in? 7A. It has 7 valence electrons. If I ask you how many valence electrons aluminum has, what column is it in? 3A. So it has 3 valence electrons. So the number of valence electrons for any main group element, that's the S blocks and the P blocks, is equal to the number of its column. So very quickly, if you have a periodic table, even selenium, so if we move down, it's under sulfur, it's in column 6A, has 6 valence electrons. The D block's weird. We don't get much into the D block in this class. And then the row number of the periodic table is equal to the highest principal shell. So again, here's this periodic table. Now looking at this, we know that in row 4, these, what I previously probably just called abbreviated electron configurations, are actually just the configurations of the valence electrons, which are really the only ones that we care about because they're the ones that react. And they predict some stuff that I've had you just memorize up till this point. Oh, briefly before we get into that though, the transition series elements, so the entire D block, those aren't valence electrons. And actually, let me just very quickly for like, so let's do selenium because I brought that one up before. So for selenium, we're going to abbreviate starting with argon, and then it'll be 4s2, 3d10, 4p4. So again, our valence electrons are only those in the highest principal quantum shell. So d orbitals represent filling core electrons because we start in the 4s row with 3d. So the d block is always in a lower principal quantum shell than the s and the p blocks. So we can only have 1 through 8 valence electrons. So if I ask you how many valence electrons does selenium have, it's 6. Even though we've got this 3d10 in here, it's 3, and our highest number is 4. So we don't count those in the valence electrons. Showing that again. If we were to write the electron configuration for phosphorus, again, we're using neon to abbreviate because that represents all the core electrons. So we're doing phosphorus, start with neon, and then it's just 3s2, right, represented by those two spaces on the periodic table. And it would be 3p3 because phosphorus is the third element in the p block. So these are slides like these. Maybe I should have mentioned this earlier on, maybe, but these are the kinds of slides because this is sort of like a procedural, step-by-step. How do you write an electron configuration, right? Just sort of laid out verbatim in words. So if you wanted to come back, this would be the place to come back to get the very, very concise version of what I've now spent, almost an hour telling you about. But we represent inner configuration, or the core electrons, with the noble gas in brackets. And again, that's the previous noble gas, so you go up a row and all the way to the end. Then our outer electrons are determined from the element's position within a particular block. And then the highest principal quantum number is equal to the row. The row number of the element on the periodic table. And our principal quantum number, n, of the outermost d electrons is always 1 less than, or equals the row number minus 1. Okay, so if we want to do an electron configuration for tin, can't do too many of these. All right, so if we want tin, and I say you're allowed to abbreviate, how would we write the electron configuration for tin? Krypton would be our abbreviation. Anybody else? What's next? 5s, because they're in the 5th row. Uh, 5s2, right, because we're past the s block. 4d10. 5p2. So again, our valence electrons are just those from the highest principal quantum shell number. So our 5 would be the highest here, so we have 4 valence electrons. All right, so now at this point, it might seem like, how do I want to say this? So we've learned basically that some elements form single types of charges. All right, so column 1 forms 1 plus. Group, I guess I call it groups on here, but the second column forms plus 2. We have some that form plus 3. Those happen to be in 3a. We also know that 7a, or 17 on these periodic tables, is 1 minus, and 6a, or 16 on these periodic tables, is 2 minus. This has more to do with the electron configurations than it does the way the periodic table is arranged. Or I guess I should say that those things are arranged that way and have those properties for the same reason, which is the valence electrons. Right? So this is all organized based on how many valence electrons they have. The number of valence electrons of the neutral element also determines the charge that they're going to form. So hydrogen is reactive, and helium is inert because of these valence electrons. I mentioned this before, but atoms with 8 valence electrons are the most stable. So if we look at helium, well, okay, helium's the exception to this because it only has 2, but it only has 2 to fill. For neon, argon, krypton, xenon, and radon, they all have 8 valence electrons. They also don't react with anything. because having 8 electrons is stable. It's balanced. It's a lower energy state. The elements then with electron configurations that are close to the noble gases are highly reactive because they either want to get one more electron to be like a noble gas, or they want to lose one electron to become like a noble gas. So hydrogen is in column 1. And I guess hydrogen's a little bit of an exception because it won't have any electrons after that. But if lithium loses one electron, so electron configuration for lithium is going to be 1s2, 2s1. If lithium loses one electron, you'll have the same electron configuration as helium. If sodium loses one electron, it'll have the same electron configuration as neon. Everything in that first column can lose one electron and be like a noble gas, and be extra stable, which is why they're the most reactive elements on the periodic table. And it's also why they form +1 charges. Because if you have one more proton, remember for lithium we have 3 protons. With this electron configuration we have 3 electrons. So protons are positive, electrons are negative charge. So when you have the same number of each, 0 charge. If lithium loses one electron, to have the same electron configuration as helium, now we've got 3 protons and just 2 electrons. So 3 plus a -2 is +1. So they all form +1 charges because they all lose one electron to be like a noble gas. Can you guess what happens in column 2? So what charges do the elements in column 2 form? +2 charge. So elements in second column just have to lose 2 electrons to be like a noble gas. So if beryllium loses 2 electrons, it'll have the same number of electrons as helium. Magnesium can lose 2 to have the same as neon. And so they all form +2 charges because they lose 2 electrons. This also applies to aluminum, gallium, and indium, where they just have to lose 3 electrons each to be like a noble gas. So group 1 is the most reactive. Group 2 is the second most reactive. Group 3 is even less reactive. This also applies to gaining electrons. So column 17 on these periodic tables, or 7a, they're 1 electron away from being neon or argon or krypton. So if they gain just 1 more electron, they can have that stable state. And if they gain 1 more electron, they'll have 1 more electron than they do protons, and they'll have 1- charges, which is why the elements in column 7a all have 1- charges. So what charge do you think, well, we know what charge, right? 6a forms what charge? It's a -2 charge for 6a. Why is it a -2? Yeah. So it gains 2 electrons to be like neon, argon, krypton, and xenon. Right? They're just trying to be like the noble gases. They got to get 2 electrons to get there. That's why nitrogen and phosphorus, and to a lesser extent arsenic and antimony, they gain 3 electrons to be like the noble gases. So when you arrange the periodic table like this, there's a bunch of stuff that sort of falls out of it. So these are most of the elements that I had you memorize. On top of scandium. Scandium forms a 3+. I think it forms a 3+, because it loses 3 electrons. And then the transition metals, because they have so many d electrons, they do weird stuff. D orbitals get wacky. All right, so the last few things we're going to cover here are some other trends that come out when you arrange the periodic table like this. So not only can we predict some of the charges of the main group elements, but we can also predict the size of an atom, at least relative to other atoms around it. So remember, if we increase our principal quantum shell, actually I think it's on the next slide. Come back to this first. So the size of an orbital depends on the principal quantum number, which doesn't change as you go from left to right. So between lithium and beryllium, or beryllium and boron, we're not changing the principal quantum number. So the only thing that's really changing is the number of protons in the nucleus. So you can think of these like magnets. So if you have one magnet, one positive magnet in the center, one north magnet in the center, that'll have some amount of strength. But if you put two magnets in the center, now it's twice as strong. So going from lithium to beryllium, we've added more positive charge to the center, which pulls in more strongly on the electrons around it. So for every proton that we add going across, the shell actually shrinks a little bit for every proton. But then when we go down to the next row, so where lithium shrinks as we go to beryllium and boron, carbon, nitrogen, oxygen, fluorine, neon. And as soon as we add one more electron and we jump up to sodium, remember, every time we jump to another principal quantum shell, we put another shell on top. So now we've sort of, I'm just mixing all kinds of analogies here, we're adding another layer to the cake. So it's getting bigger because we're adding another shell on top. So every time you go across a period, you're adding protons. Not adding to the shell, it gets smaller. So left to right, atomic size decreases. If we move down a column, we're adding those shells. So n equals 1 is going to be smaller than, n equals 2, smaller than, n equals 3, and so on. And that change is bigger than adding more protons. All right, so there's a couple ways that you can remember this. You do exactly like this periodic table does here. Size decreases as you go across, but size increases as you go down. I like to think of it like cesium is the biggest. So if we get closer to cesium, we're going to have a bigger atom. If you get farther away from cesium, closer to neon, we're going to get smaller. So moving in this direction across the periodic table gets bigger. Moving up this way gets smaller. Okay, so for lead, so we have lead and polonium. Which atom is larger? Lead. Lead's closer to cesium. Lead is larger. If we have rubidium or sodium, which one's larger? Rubidium. And these are exactly like the kind of question that I would ask on an exam. If we have tin or bismuth, tricky. Bismuth, yeah. Jumping down, you add a whole other shell. So that's more important. Okay, for fluorine or selenium. Selenium. Yeah, that one's not so tough. So for atomic size, moving down is more important than moving across. There's another trend that we can predict here, which is ionization energy. And essentially, ionization energy is how much energy it takes to steal an electron from an element. Specifically measured for atoms in the gaseous state. So if we want to take sodium's electron, we have to input some amount of energy to steal that electron away. So the ionization energy increases as you move to the right across a period. So left to right on the periodic table. Is there something else here? Oh, okay, yeah, so we'll talk about that next. So if you think about this, do you think it's easier to remove an electron from sodium or from chlorine? Why would it be easier to remove an electron from sodium? Because it wants to lose an electron to be like a noble gas. Yes, exactly. But chlorine, it wants to gain one more electron to be like a noble gas. So it's going to fight you really hard if you try to steal one more of its electrons, because then it'll be 2 away. So group 7A elements are very difficult. That's the column that chlorine is in. Very difficult to move and remove an electron. But group 1A will give it up easily, because that's the direction they want to go anyway. This idea of magnets, so again, sorry, that's why moving the left side of the periodic table, easy to remove electrons, gets more difficult as you go to the right. As you move down a column, we have something different taking effect. As you move down a column, again, we're adding shells of electrons on the outside. If you think about magnets again, the farther you get away from the magnets, or the farther away you pull the magnets apart, the weaker it gets. So that's what's happening here. Our outermost electrons, for every shell that we add, are farther away from the pull of the nucleus. So they're easier to remove. So as we move down a column, adding shells of electrons, it gets larger. Those electrons are farther away from the nucleus. It's easier to pop those off. So ionization energy and atomic size are opposites. So as your atom gets smaller, it's harder to remove the electron. As your atom gets larger, it's easier. So again, looking at this here, right, moving down, again, we're getting bigger. So the ionization energy decreases, takes less energy. As we move right, ionization increases, or energy increases. So between magnesium and strontium, which electron's easier to remove? This is the opposite of, higher ionization energy. Which one's more difficult to remove? Yeah, magnesium, sorry. For indium or tellurium, which one's going to be? Yeah, indium. For carbon or phosphorus? Phosphorus is going to be more difficult. Because phosphorus, higher energy. It's down a row, so it's a larger shell, but it's also closer to being a noble gas. So this is where moving left to right is more important than moving up and down. So in every way, it's the opposite of atomic size, atomic size. It's phosphorus. So for D, fluorine and sulfur, fluorine, yeah. Because it's higher and it's smaller. All right, the last trend we're going to talk about then is metallic character. And this one's easy to remember if you remember atomic size, because it's the same. Metals tend to lose electrons. Again, remember group 1 and group 2 are both metals. And they both want to lose 1 and 2 electrons respectively to be like noble gases. Nonmetals, on the other hand, tend to gain electrons. So this is kind of going back a little bit, but remember everything to the right of, on these periodic tables, the dark zigzaggy line, those are nonmetals. And that includes fluorine, chlorine, and bromine, which we learned gain electrons. those are less metallic. So metallic character decreases as you move right across a period. Metallic character decreases as you move right, increases as you move down. And it's the same as atomic size. Same trend as atomic size. So moving down, it increases. Moving to the right, it decreases. And if you've already got this locked in your mind that these are all nonmetals, and the rest of these are metals, as you move farther away from the nonmetals, you get more metallic. As you get closer to the nonmetals, you get less metallic. All right, so for tin or tellurium, which one's more metallic? Tin. And even on this periodic table, these are in purple. If they're purple on there, those are metalloids. So silicon or tin? Which one's more metallic? Tin again. Tin for the win. What about bromine or tellurium? Tellurium. Selenium or iodine? Same trend as atomic size, so going down a row, more important, although very, very slightly, if any, be roughly the same. Okay, that's it. That's chapter 9. So it's going to lay the groundwork for what we're talking about. I'll go over the Lewis dot worksheet again in lab, but we'll actually cover that in class next week.